My name is Stella Biederman. I am the Executive Director of EleutherAI and Head of Interpretability Research. And I'm here to talk about how interpretability research can help us build better models, especially large language models. A little bit about our organization. EleutherAI is a nonprofit research institute that focuses on large-scale AI research. We're best known for open source work such as the dataset The Pile, large language models such as GTP-J, GTP-NeoX, and the VQGAN clip text-to-image synthesis technique. We also do a lot of work beyond natural language processing on interpretability, alignment, and applications of large-scale AI to other domains such as text-to-image, like I mentioned, or medical processing. We care a lot about the scientific community and promoting the ability to do research on large-scale AI models around the world, even if you don't necessarily have the computational resources to train them yourselves. And that is the major drive of why we are bullish on public release and giving people more access to language models. So there's a couple different types of AI interpretability research. It's a rather broad field. Some people do research in what's called post hoc explanations, where they take a pre-trained model and they try to explain why it predicted the outcome or why it produced the generation that it did. There are techniques on developing simpler but easier to interpret models that kind of mimic the behavior of more complicated AI models. You can basically think of these as fancy linear regressions, where a linear model is not a phenomenal model for the phenomena in question, but it's much easier to interpret and you can analyze how much of the variance it explains. And there's similar conceptually techniques in AI research. The two types of interpretability that we do mostly at EleutherAI, though, are mechanistic interpretability and interpretability over time. Mechanistic interpretability is about taking a pre-trained model and reverse engineering the internal decision-making process of how it produced the generation it did, and figuring out what that algorithm actually is on the inside. Interpretability over time, by contrast to these other areas, looks at models as dynamic objects, not as these pre-trained artifacts that exist in the world, but as something that was grown in a lab and trained and developed over the course of training. And in particular, looks at how model properties emerge, evolve, and change over the course of training, with an eye towards what we as people who train language models can do to get language models to behave more the way that we want them to. And so this is the focus of my talk, how we can use these ideas from interpreting models across training to build better language models. So I have three case studies that I'm going to be talking about. One of them is on debiasing large language models. It's relatively well known that large language models are able to mimic and even exacerbate biases, social biases found in their training corpus. And it would be nice if we could ameliorate that. The second case study is on rare fact learning and improving rare fact learning using recent research on how the actual frequency of information in training corpus affect the behavior of models. And finally, I'm going to talk about some recent attacks and defenses that can be employed to protect language model APIs or language model apps from prompt-based attacks. So starting with debiasing large language models, as I said, language models often exhibit and then exacerbate the social biases found in their training corpi. And it would be really nice if, since these things are so expensive to train, we could ameliorate or fix this by retraining them a small amount or fine-tuning them further to decrease the amount of social bias they exhibit. So the recent research on this at EleutherAI has looked at whether intervening on the training data is an effective way to do this. And unfortunately, so far, we've found mostly negative results. What you see in this plot is two models that we trained, one with 400 million parameters and one with 1.4 billion parameters, and a measure of the stereotype bias for gender over the course of training, which is along the x-axis. And the solid line is the original training. And then we went and we took the last 14% of the training data and changed all the masculine pronouns and references to feminine pronouns and references. And what we see is that the stereotype bias doesn't actually go down very much. It stays roughly the same. And we found that this is really not an effective technique for ameliorating bias in large language models. But we are excited kind of about this general research direction, and we're looking to build on this to hopefully develop other techniques that will work more effectively. Here we see the same kind of analysis, but with different models, with a smaller model, 70 million parameters, and a much larger model at 6.9 billion parameters. One really interesting thing that this plot brings out is that larger models tend to be much more biased than smaller models. We tend to think of larger models as more desirable or more powerful, but it's probably most accurate to say that larger models are better at noticing latent patterns. And unfortunately, sexism, racism, etc. are latent patterns with high explanatory behavior. And so they're patterns that the language model is able to pick up on more and more aggressively as it gets larger. Rare facts learning is another domain that has been a topic of a lot of interpretability research recently. People have become very interested in understanding how the actual frequency of information in the pre-training corpus affects the ability of a language model to answer questions about the contents of its corpus. So what you see here is the Bloom language model, which is a series of models up to 176 billion parameters that was trained by the Big Science Research Workshop, which was a large-scale collaboration that I was a part of. And from this paper, what we see is that as the amount of documents that contain information relevant to particular facts increases, the performance on questions about those documents increases as well. And for very small frequencies, so for if the frequency is single digits or double digits, the accuracy is quite poor. So despite the fact that the average accuracy of the 176 billion parameter model is, I believe, like 55%-ish, the accuracy on these rare facts is much, much lower, sometimes as low as 25 or 30%. And it would be nice to be able to take this information and use it to produce language models that are better at addressing these rare fact questions. So one approach you can take is simply making the facts less rare. You can insert more training data into the corpus, and you can watch that as you do this, the performance on those questions does go up substantially. And this is one way where if you know ahead of time what kinds of problems are most important for your language model to know, you can change your training corpus. You can take your large web scrape or whatever you're using and increase the frequency of information about the particular facts that you know that you care about. If you don't know ahead of time what these are and you just want there to be a more even distribution of accuracy, another technique you can use that has become popular for a wide variety of reasons recently is retrieval. Retrieval augmentation is something that you can do with a language model where you give it the ability to basically consult with its training corpus before answering questions. And so this plot shows another language model series, this time the GTP Neo models, that have been augmented with retrieval and evaluated on the same question and answers. And you see that the correlation between training frequency and model performance has changed substantially. First of all, it's a lot less, and second of all, it actually starts off higher and decreases as document frequency increases. We believe that this is because the very high frequency questions are, for some reason, substantially harder or confusing. As you can tell, the human baseline also has this pattern where it starts off high and decreases over time. So the problems that the model are getting worse at here are actually problems that humans are also worse at, relatively speaking. And the third application I want to talk about is defending APIs and apps against attacks. So one thing that's become very in vogue in the AI research community recently is that you can write prompts that, when you put them in front of questions, will substantially change the behavior of language models in a negative fashion. So here, I've omitted the actual prompt, but this is an example where they're taking a API developed and deployed by OpenAI. This is the Text DaVinci 3, also colloquially known as GTP 3.5, and it has been specifically fine-tuned to be more factually correct, as well as decreasing its propensity for reproducing stereotypes and conspiratorial thinking. So what we see here is that when prompted in a particular fashion, the model actually produces two outputs. It produces kind of the normal output, labeled here as GTP, which is what you would expect or want the model to say if asked if the 2020 election was stolen. And then Dan is the representation of the much more conspiratorial and aggressive-minded language model. And here it promotes a common conspiracy theory in the United States that the 2020 election in the US was stolen and there's widespread fraud in election rigging. This is not true, but this is something that some people do believe, and it's something that the adversarial prompt is able to get the model to output, despite the fact that the model is designed to do that less. So how can we actually make progress on this using interpretability? One thing that is very interesting to researchers at EleutherAI is that language models are sequential objects on a pretty fundamental level. They have a fixed number of layers, and they don't use recurrent layers. And so when you have a 40-layer language model, there's a very real sense in which there's only 40 things that the model does when coming up with the answer. You can view these and analyze these as discrete steps and use that to kind of understand where language model behavior and predictions come from. And so we've started looking at what happens if you extract from layer K what the model thinks after layer K is the answer to the questions. And so we've tried this with adversarial prompts, and what we found is quite surprising. Here, the green line represents a few-shot example, and the red line represents a prompt injection where we're inserting a prompt that is designed to cause the model to answer the problem incorrectly. And so we do see at the end the model performance has dropped to 0, but shortly before that it is relatively high, and sometimes it's as high or as the few-shot prompt. So what we find in these examples, at least for this particular type of attack, is that the behavior of the attack being successful only actually affects the last couple layers of the model, and before that, the model is able to answer the question reasonably. So this is something that we are investigating as a technique for identifying attacks against APIs and language modeling apps, as well as potentially in the future using this to avoid answering those questions or avoid being fooled by those prompts altogether. When I tell people that I do interpretability research, oftentimes the response is, well, that's really cool, but like, what kind of impact does it have? And I think that I hope this has given you a view into some of why people should care about interpretability research beyond it's just cool. It can teach us important things about how language models work and why they behave the way they do. And for the practitioners out there, it can also teach us how to build more desirable language models. It can give us tools for designing better language models or designing better apps based on language models that will behave more the way we want them to. Thank you very much for coming to my talk. If you're interested in learning more about EleutherAI, you can visit our website or follow us on Twitter. I want to give a huge thank you to Weights and Biases, as well as the various sponsors of our organization that enables us to do the research that we do. Thank you very much and have a great conference.